Welcome to lecture series on heterocyclic chemistry. In this lecture series, we are going to discuss about the chemistry of indole. In previous lecture, we have seen few methods for the synthesis of indole. In this indole lecture series is divided into three parts as far as the synthesis of indole is concerned. Here there is a list of total nine name reactions involved in the synthesis of the indole. The first five reactions we have already discussed in the part 1. Now in this particular lecture we are going to discuss these three named reactions. One is a Bartoli indole synthesis, Gassman indole synthesis, Larock indole synthesis, and apart from these three named reactions we will also discuss the applications of benzene chemistry for the synthesis of indole, and the last lecture after this will be dedicated to the Fischer indole synthesis. Now before starting for the actual discussion on these three methods, that's a Bartoli indole, Gassman indole and Larock indole synthesis, which is a part of today's discussion, let us have a revision on what we have learned in the previous class. In previous class we have completed five synthesis of indole. One is a Rizet indole synthesis, the Medlang synthesis, the Bessler indole synthesis, Nenezescu indole synthesis and Bartoli-Limgruber indole synthesis. Now, in all these cases, we are going to start with the appropriately substrate benzene. In these three methods, Rizet, Medlang and Batko-Limgruber, we are starting with the orthodisubstrate benzenes, and therefore we have to make an arrangement for only one carbon atom here. So diethyl oxalate and this N,N-dimethyl formamide acetal type of the substrate was utilized. Then it undergoes a condensation to form this ketoester. Here it forms an enamine, and then under reductive cyclations we get the indole molecule. Similarly, in the Medlang synthesis, we are starting with the also orthoalkyl anhalides, which under high temperature as well as under strong basic conditions forms here indole. Then in Bissler indole synthesis, we start with the alpha haloketone and then aniline. We get here alpha aryl amino ketone, which undergo Preda-Krupp type of the cyclization to form this indole. Nenezescu synthesis is particularly useful for the synthesis of 5-hydroxyindole, which is very abundant in the natural products. It involves a condensation of benzoquinone with enamine to form here 5-hydroxyindole. So these five methodologies we have discussed in the previous class. Now in this particular lecture we are going to discuss about the Bartoli indole synthesis, Gassman indole synthesis and Larock indole synthesis. Bartoli indole synthesis is a very meticulous synthesis of indole involving a reactions of again orthonitrotoluene with vinyl magnesium bromide. It forms here 7 substrate indole. This CH3 is not taking part in a reaction. Here it is getting cyclized on this side of the portion and we get here 7 substrate indole. It is observed that 3 or 4 substrate nitrobenzene provided either no indole products or indole in poor yields. This reaction is particularly successful when the ortho position is blocked in nitrobenzenes. Now the mechanism of this reaction is very interesting. Here 3 equivalents of the vinyl magnesium bromide is required. One equivalent acts as a reducing agent which converts nitrobenzene to the nitrosobenzene. Another molecule acts as a nucleophile which is utilized in the final indole framework. The third equivalent acts as a base which is useful in the rearomatizations of the aromatic ring. So this is the reaction mechanism of the Bartoli synthesis. In the first case, it attacks on this oxygen and we get here vinyl ether type of the substrate, and this is decomposed. It's vinyl alkoxy group is a very good living group, and here we get conversions of nitrobenzene to the nitrosoarine. So reduction reactions occur due to its reaction with the first equivalent of the vinyl magnesium bromide. Then the second equivalent of the vinyl magnesium bromide gets added across this N double bond O, where the oxygen gets added to the vinyl group. Then we get here this intermediate, and this intermediate undergo a very characteristic reactions involving a nitrogen oxygen bond cleavage as well as a carbon carbon bond formation, and it is proceeding through the 3,3 sigma tropic rearrangement. It's a pericyclic reactions involving a concerted pathway. It is a very important reaction as far as the mechanism is concerned. Here two things are happening in one pot. Carbon carbon bond is established here as well as the nitrogen oxygen bond is cleaved, and then here it undergoes subsequent cyclization to form here this 5-membered ring, and it is described as a 5-exoteric according to the Baldwin nomenclature, because a 5-membered ring is formed by attack on nucleophilic nitrogen on the trigonal carbon and it is opening on outside here, and that's why it's a 5-exoteric cyclization. Later on, third equivalent of the vinyl magnesium bromide helps to maintain the aromatizations of this benzene ring, and then aqueous workup results in the formations of here 7 substrate indole. So this is a very interesting mechanism of Bartoli indole synthesis, where three equivalents of vinyl magnesium bromides are required. One act as a reducing agent, second act as a requisite nucleophile, and the third one is acting as a base. This Bartoli indole synthesis is successful only when the ortho positions of the nitro group is blocked here. So ortho substrate nitrobenzenes are the substrate here, and as a result of that, the 7 substrate indole can be prepared with the help of Bartoli indole synthesis. So its reactions with the vinyl magnesium bromide, we get here this 7 substrate indole here. Here also we get a 7 substrate indole. Then here post modifications of this phenolic ether is carried out by some preliminary reactions. Here the reduction occurs, here debenzylation type of the reaction will occur, and then in presence of a base it will form a carbon-carbon bond. Similarly here one can form a decorated orthonitrobenzene by using lithiation chemistry. Here exchange of bromine will occur. Here it will be lithiated, and then its metallation will occur here, and then we'll get a carbon-carbon bond forming reactions. And then its reactions with vinyl magnesium bromide will give you a 7 substrate indole. Similarly, here also the 7 substrate indole is formed, and relatively the yields are good here. 88% here is a 68% yield of 7 substrate indole. Now sometimes we may not require a 7 substituent here. So in that case, one can use here bromonitrobenzene, orthobromonitro type of the substrate. So if you perform here Bartoli indole synthesis, we'll get here 7 substrate indole, and later on this bromine can be removed by tributyltin hydride reductions by using azoisobutyl as an initiator to form here 94% yield of this indole molecule. So in Bartoli indole synthesis, we have seen reactions of the vinyl magnesium bromide with the orthosubstrate nitrobenzene. Now the next methodology is again based upon the pericyclic reaction here. This it is called as a Gassman indole synthesis. In Gassman indole synthesis, there is a sequential additions of tertiary butyl hypochlorite, uh, then beta ketosulfide, as well as base. So there is a sequential addition of these three components to the aniline to form 3-thioalkoxy-indole. Here is a example given: 69% yield of the thioalkoxy 2-methyl indole is formed here. Now this reaction is successful because of the sulfur chemistry, and sometimes we may not require a sulfur. In that case, the sulfur can be removed by using Rane nickel desulfurizations. So in this way, we have prepared here a 2 substrate indole. Here 2-methyl indole can be prepared with the help of Gassman indole synthesis. The mechanism of this reaction is very interesting to discuss. First of all, a tertiary butyl hypochlorite, which is a source of Cl plus, will perform here N chlorination, and this particular reaction is carried out at very low temperature. So after forming of N-chloramine, it reacts with the sulfur nucleophile, and chlorine is displaced here, and we get a sulfonium salt. And this sulfonium salt is to some extent acidic in nature, so its reactions with the triethylamine will generate here a carbanion. This carbanion is stabilized by now sulfur plus positive charge sulfur, and that's why it is called as an ylide. Now this ylide undergo a very crucial pericyclic pathway. It is called as a 2,3 sigma tropic rearrangement, or it is also called as a Somlet-Hausser rearrangement. Through this 2,3 sigma tropic rearrangement, a carbon-carbon bond is established, as well as a nitrogen-sulfur bond is also cleaved here. Then in the subsequent transformation, we get aromatization as well as a cyclization, 5-exoteric cyclization to form the indole derivative here. And then this will undergo a dehydration to form 3-thioalkoxy indole molecule. So in this case, the success of this reaction is due to the sulfur ylide formation. Sulfur ylide undergo a very characteristic reaction called as a 2,3 sigma tropic rearrangement. That's a Somlet-Hausser rearrangement, and that's why this reaction is successful. Now these are the various examples. One can start with the appropriately substrate benzene ring, and a wide range of substituents can be tolerated in the reactions, and the yield of the indole is also achieved in very high yield as far as this Gassman indole synthesis is concerned. Then this methodology can be extended to the aryl ketone thioethers. if it is treated with instead of this one beta ketothiosulfide, if we do this perform here reactions with the ketone aryl ketone, then introductions of two phenyl group can be achieved at two positions of indole. Now if this alpha position is occupied by an alkyl group here, then again here Gassman indole synthesis is successful, but here we do not get a completely aromatized system. And this mechanism of this reaction is again similar to what we have seen in previous cases. So here di here this is a saturated carbon, it's not a completely aromatic system, it is called as indolinine derivative. And this indolinine derivative can be reduced with lithium aluminum hydride to form dimethyl 2,3 dimethyl indole. This is also 2,3 disubstrate indole derivative. So in this way, we have learned two important reactions. One is a Bartoli indole synthesis and is a Gassman indole synthesis. And in both the cases, what is important is a 3,3 sigma tropic rearrangement and a 2,3 sigma tropic rearrangement. Here in Gassman indole synthesis is a sulfur halide is there. It's a 2,3 sigma tropic rearrangement. Whereas in Bartoli indole synthesis is a 3,3 sigma tropic rearrangement. And the next one here is a Fischer indole synthesis. Here is also 3,3 sigma tropic rearrangement that we will discuss in a previous class. So through this pericyclic pathway, it is very sure the carbon-carbon bond is established here, and the heteroatom-heteroatom bond, particularly the nitrogen-nitrogen, nitrogen-oxygen, nitrogen-sulfur bond is cleaved. So these are very interesting kind of processes involved in the synthesis of the indole. Now the last methodology of this lecture is a Larock indole synthesis. It's to some extent a modern method for the synthesis of indole. With the advent of transition metal catalyst in organic synthesis, the heterocyclic chemistry is completely revolutionized. And here is one of the notable synthesis of indole. It is called as a Larock indole synthesis, reported in the year 1991. It is called as a heteroannulation reaction. Here we get annulations of the benzene ring, and we have to start with the orthoiodoaniline. When this orthoiodoaniline is treated with the alkyne in presence of a palladium salt and some base, we get here formations of indole. This reaction is flexible because one can vary these components here, as well as one can start with the substrate benzene ring also. These are some of the classic example of Larock indole synthesis. Here the pH group, generally the bulkier group between R2 and R3, it is bulkier group is nearer to the nitrogen here. It's at the 2 position. Here the 2-phenyl indole is achieved here. Here again we get the synthesis of indole in a 98% yield. And this methodology can be extended to the synthesis of benzopyrrone. Instead of orthoiodoaniline, if you take orthoiodophenol, again we are getting a benzopyrrone derivative that is in a 90% yield. Now let us discuss the mechanism of this reaction. It's very interesting reaction. It's a transition metal catalyzed reaction, and everything occurs on the coordination sphere of the palladium. And for that, we have to this palladium will bind this organic ligands on its coordination sphere through certain processes like oxidative addition, ligand exchange, and later on it will form a carbon-carbon bond forming reactions as well as a carbon-nitrogen bond forming reactions. So let us see how reaction proceeds. In this case, palladium 2 is a catalyst here. Palladium 2 species is involved here. So palladium 2 undergo pre-activation process by using some bases or some ligands like triphenyl phosphine, and we get here palladium 0 species. Palladium 0 species contains 14 electrons in the outermost shell. It's a coordinatively unsaturated, and this palladium 0 species can react with the chloride. Sometimes the lithium chloride is added in the reaction, and it is necessary for reproducibility as well as for high yield of the reaction. So one of the ligand exchanges with this, and we get here attachment of chlorine on the coordination sphere of the palladium. Now again the palladium is in a zero oxygen state with 14 electrons, and therefore it is a coordinatively unsaturation. It will try to achieve the 18 electron configuration. So it undergo an oxidative addition process. The palladium is inserted between carbon and iodine, and we get here attachment of one organic ligand to the palladium here. Here for this it is utilizing the 2 electrons, and therefore it is oxidizing from palladium 0 to the palladium 2. It is a 16 electron species now. Now this 16 electron species will undergo ligand exchange. These ligands are very labile, and on exchange this palladium will bind to this alkyne. Now after this is a very important stage of the mechanism where we find that the palladium has bound two reacting organic ligands. One is a aryl and another is a alkyne. Then here the migrations of one organic ligand from palladium to the alkyne occurs here, and the process is called as a carbopallidation. And in this carbopallidation, the largest substance usually at the R2. So here R3 should be of minimum steric size, and here we get a pallidation reactions. This between the palladium and the carbon, between the palladium and this carbon atom, this alkyne group is inserted. It is called as a carbopallidation. And then this nitrogen also coordinates with the palladium. Now in this way, these two nitrogen and carbon bond is about to form here, and they are bound to the coordination sphere of the palladium, and later on the palladium removes from its coordination sphere through a process called as reductive eliminations, and we get here indole synthesis. So, and again the palladium zero is generated and this catalytic cycle continues here. It's a very important mechanism, and it gives an opportunity to revise certain basics in the organometallic chemistry, and therefore the student should undertake writing the mechanism of Larock indole synthesis. Now here there is some classic example of some transition metal catalyzed indole synthesis. Here is a enamine is formed very easily in presence of an acid. Starting from orthobromoaniline on reaction of the diamidone forms an enamine, and this enamine now undergo a C-C bond coupling reactions with the help of palladium. To some extent it is we may call it as a Higgs coupling reaction. Similarly here a nitrogen carbon coupling occurs with the palladium, and then the carbon-carbon bond forming reactions are observed here. Here also we observe here insertions of palladium, then we'll get a carbon-carbon bond, and later on it will tautomerize to this. Now here is a apart from this transition metal catalyst in organic synthesis, here is a applications of benzene chemistry for the synthesis of indole. This can be prepared very easily by reactions of cyclohexanone with the appropriate amine, and then this on reactions with the sodamide generates here a benzene. Sodamide is a very strong base. It generates a benzene, and to that benzene the carbanion is added, and we get the indole derivative. Similarly, here also we get here a benzene. Here the fluorine and hydrogen, both of them are removed. We get a benzene here, and here the lithiation occurs. So internal nucleophile. Here the lithiation occurs at two positions, one at this one and this here. Then this lithiated carbon atom attacks on this triple bond, and here we get again carbanion. This carbanion can be trapped with the help of acetone, and we get here substrate indole. So benzene chemistry is sometimes also very useful in the synthesis of the indole molecule. So in this way, we have learned three name reactions for the synthesis of indole. One is a Bartoli indole synthesis, which employs vinyl magnesium bromide as a substrate. Second involves a Gassman indole synthesis where the sulfur halide chemistry is involved. Next methodology is a Larock synthesis where the palladium chemistry is employed. It's a carbopallidation, it's annulation, heteroannulation reactions. So in this way we have learnt these three methodologies and some examples of benzene chemistry for the synthesis of indole. Now let us see some problems on this indole chemistry. Students should undertake some practice of writing the reaction mechanism. Here is a mechanism of the Gassman indole synthesis. Then this is a Bartoli indole synthesis. This is also the Gassman indole synthesis. Its details are already discussed in a previous slides, and therefore students should try to write down the mechanism of these reactions at home. Then the second variety of the problem is spread the product of the following reaction with suitable justification. Here the here the Bartoli reaction is successful with the orthonitrobenzene, and sometimes this ortho portion is not necessary, and therefore we start with the bromo compound. We get a 7-bromo indole derivative here. Later on this bromine can be removed with tributyltin hydride. We already discussed it here. Then this is a Higgs type of the coupling. This is also the Higgs type of the coupling. That's applications of transition metals for the synthesis of indole molecules. So in this way, we have completed the discussions on three important name reactions for the synthesis of indole. In the next lecture, we are going to discuss about the Fischer indole synthesis. Thank you very much for watching the video. Thank you very much.